great to have Raemi Monasson here. I know Raemi from his work on applying statistical physics to problems of random satisfiability problems, and he's shown how ideas from physics and statistical physics, while they might not always be complexity theorems and so on, they give real insight. And Raemi is also really good at giving connections between the statistical physics approach and computer science, so we can talk somewhat the same language, which is great. So now it's a new topic on learning Boolean threshold functions.
Okay, so thank you to Paul and Russell for this kind invitation to talk here. So I want to tell you about works which have been done actually in the last, I would say, 20 or up to 25 years in statistical physics, and which are related to the learning of with Boolean threshold functions. And some of this work have been done with Simona Coca, who is here, and more recently with Ran Rubin and Chaim Sampolinsky from the Hebrew University in Jerusalem. So I'll start with a very short biological motivation. I just have a couple of slides on why we were interested in this kind of problem here and how to apply statistical mechanics to these problems. And then I'll turn to the blackboard and try to tell you how the calculation can be done in order just without, I don't want to show too many technicalities, but I want to go into details also to show how statistical mechanics can have a different, let's say, perspective on learning problems which are studied also in computer science and in machine learning and on other disciplines. So simple motivation, first one was actually coming from neurobiology. And as you know, neurons, at least most neurons, not all of them, but most neurons, have a very specific activity which is made of spikes, which are very, let's say, localized, highly localized electrical activity in time, which lasts for, let's say, 1 millisecond, something like that. And the potential of a membrane, of a difference of potential between the inner part and the outer part of the membrane of a neuron has a huge increase for a very short amount of time, and this is called a spike. And in between spike, there is kind of silent no activity, or let's say a very small activity. So the neuron may be, to some extent, modeled by a binary variable, which is 0 if the neuron is silent or 1 if it's active. Most of the time, the binary variable is equal to 0. So from the 1920s, from the first experiments done by people in neurophysiology, the question was asked that how is information encoding in the electrical activity of a neuron? So there were famous experiments from 1926. And the first experiment showed, for instance, people attach a weight to a muscle of a frog and measure the electrical activity of the nerves which are attached to this muscle. And what they showed is that the firing rate, which is the amount of spikes per unit of time, which are triggered which are measured if you look at the electrical activity of the nerves, increase proportionally, or let's say increase monotonously with the weight which is attached to the muscle. So the first ideas about the coding of the information by the neuron was that actually the firing rate and not the precise timing of the spikes is what matters. This is how information is conveyed. And that makes a lot of sense, because if a neuron is stochastic, then the timing here could change from, let's say, if you repeat the experiment twice, and you would say that you would like the same information to be converted to the central nervous system, for instance. That means that this stochasticity shouldn't matter too much. And the firing rate, which is an average quantity, should do the job. Okay, it's a better way to encode information.
When you say firing rate, over what time scale are you measuring the rate?
Okay, so it depends on the kind of experiment. I will show in another slide. So generally over a few, so all frequencies we are looking at are of the order of the hertz here. So it will be over, let's say, 100 milliseconds, over 1 second, or 10 seconds maximal time. Okay. So, and this was the first model of neuron, which is called the Perceptron, which dates back from, to my knowledge, to Rosenblatt from the 1950s, where we have a neuron here, and this neuron gets some inputs, and the inputs will be the firing rates of, let's say, n input neurons, which are real numbers going from, let's say, called R1 up to Rn, but just the average value of this binary activity here over time. And what the neuron does is just a linear sum of these different firing rates with coefficients which depends on the input, J1 up to Jn. Compare the sum to some threshold, and if the sum is above some threshold, then a spike will be fired. Otherwise, the neuron will remain silent. So it's a linear Boolean threshold function. So one question which was asked at the beginning is, what are the, let's say, the computational capabilities of this neuron? So for instance, if we have a set of inputs and outputs, so we have a set of input rates here and an output which may be either silent or active. So, so what are the weights here, the choices of the weights which satisfy this mapping, which might map the input onto the outputs? And more precisely, if we have many pairs of input-outputs, can we find weights which, let's say, map the inputs onto the right outputs? Okay, so it's a learning problem.
One quick question. So the firing rates are things which they're like rates over time. Is there a notion of the output? Are we thinking of that as like if the output is 1, is it like firing continuously or firing occasionally? Or
Oh, okay. So here, there is no notion of time here. You see,
rates are like quantities that are defined in terms of time.
yes.
The output.
So basically, you have let's say an input here, which would be the set of the spikes of the first neuron over some interval of time. You just compute the average firing rate, so the number of spikes divided by time, and that would be the first input here. And then my question, and now time has completely disappeared. And the question is whether the neuron here will be silent or active at some point, you see?
Okay, so there's no notion of time?
No notion of time.
It's either always firing, okay, just no notion of time.
No notion of time. So that was that's the simplest model you can think of, okay? But actually this model is the newer experiment showing that actually situation is more complicated than that. So here I just report some experiments which were done 2 years ago by Markus Meisser and Tim Gollish in Harvard. And here is the experiment. So these people take a salamander, extract the retina from the eye of the salamander, put it on a surface with multi-electrodes, and measure the activity of the different ganglion cells in the retina. So here I show only 4 different cells. So the circles corresponds to what is called the receptive field, the center of the receptive field, which is the region on the retina to which the particular ganglion cell you measure is most sensitive to. Okay. So there are 4 different cells that you can see, and this is one stimulus presented to the retina with a computer screen. So the stimulus is very simple. You have a dark strip and 2 bright strips. Okay. And now this is the stimulus presented here for some amount of time. So the time is measured here. So you see it's about 100 milliseconds, basically. And what you can see here is as a function of time, if you look at the first line here, you can see the activity of cell 1. So each time you find a dot here, it means that cell 1 is firing a spike. And same thing for first line, cell 2, cell 3, and cell 4. Now the same experiment is repeated, and you get the second line here, and you see that there is obviously some correlation with the first line, but the precise timing is not exactly the same. Okay, so there is some stochasticity in the output. Okay, and the experiment was done many different times, so you can see different stimuli here, 8 different stimuli, and the answer for of the different cells, and each experiment was repeated about 12 to 15 times. I don't remember exactly the number of lines here. So what these people measure is they measure the information quantity of information you have about the stimulus if you look, for instance, at the firing rate of the different cells. Okay, so if you look at cell 1, then you count the number of spikes divided by the amount of time. So let's say the number of spikes. That gives you a quantity, and the distribution of this quantity depends on the stimulus. Okay, so you can measure some mutual information between the stimulus and the number of spikes of cell 1. That's a mutual information, which at most is equal to 3 bits if you have 8 stimuli. But you can do also something else. You can look at some information contained in the timing of spikes. So one particular one particular quantity you can look at is the timing of the first spike, or let's say the latency between the first spike which is fired and the time at which the stimulus is presented to the retina. So you present the stimulus to the retina, and then the cell will fire a spike. And there is a delay, which is called latency. This latency also is specific to the stimulus. Or let's say it has a distribution which is specific to the stimulus. So you can extract also some mutual information. And here is the plot, and you see that the latency seems to give more information than the number of spikes. So the timing matters. The timing conveys some information about the stimulus, but the number of spikes does not have them. So, and then I will finish with another experiment. So this experiment was done some years ago. So here in this experiment by these people, Exter and collaborators, a rat is on a track between two extremities here. And what the people measure, they measure the activity of one particular cell, which is called place cell, in the hippocampus of a rat. So a rat is moving, and the activity of a cell is measured as a rat is moving. So the place cells have the particularity, or let's say, firing depending on the position. So the firing pattern of the place cell depends on the position of a rat in the environment. So for the particular cell which is measured here, you see that the firing rate, which is color, you have a color here, it's a color coding. The firing rate is higher in one particular location on the box, let's say, on the environment here. And it's small if you are far away from this particular location, and it's peaked around this particular location. OK. And now here's the activity which is measured here. And so you see that train of spikes with the maximum around this location here. I mean, the scale is a little bit shifted, so the maximum is here, correspond to this region here. And so what the people measure is how the firing rate, let's say the maximum firing rate you get, is related to the location. All right, okay. And it seems that how also something which is very important so in the hippocampus is that the hippocampus has some overall activity, global activity, which is called a theta rhythm, which is a slow oscillation of the order of few hertz, okay, which serves as a clock, say an external clock. And what these people say, I don't want to get too much into the details, is that actually there is the coding of the information. I mean, there are different information which are important here. So one thing is the velocity of a rat, another thing is the location of a rat. So it seems that the firing rate is conveying information about the velocity of a rat, okay? And it depends on the velocity of a rat. While the phase between the spikes which are fired and this clock here tells us something about the location of the rat. So there is no simple answer to how the coding of information is done. It's not either rate coding or time coding. It's something in between. Both information are useful. So that's why the simple model of the perceptron I showed before is not an adequate model anymore. Okay. Certainly, time is very important here. Okay, so this is all I wanted to show on the slide. And so I would like to show you how some techniques from statistical mechanics can be used in order to first study the perceptron, which is well studied, and many results have been known for many years, many decades. But different insights can be gained. And I will go in the second part of the talk to the analysis of this time-dependent neuron, which is called a tempotron, which is basically an integrate and fire neuron, where decisions are taken according to the timing of the spikes, of input spikes. Okay, so in the first part, I will consider the perceptron, which is just a linear Boolean threshold function. So we have some inputs, numbered 1 to n. And these inputs are connected to the output sigma here through some weights. And I use a ±1 representation here. And the output will be simply the sign of the weighted sum of the inputs minus some threshold. Let's see. I don't know how to call it. Let's say threshold here. And the inputs here are just the firing rate I mentioned before. So they can be real numbers. They can be also binary numbers. They could be anything, OK? So in the following, I will consider the case where the threshold is equal to 0. And this can always be done by adding, for instance, a fake input here equal to -1 and a coefficient here, J0, equal to minus or to plus theta threshold, OK? So I will always consider that. So the learning problem I am interested in is, assume I'm giving a set of inputs and outputs. OK, and the corresponding output. And actually, that would be a pair of input-output here. And assume I'm given a certain number of these pairs of input-outputs, and I will label the different input-output pairs with an index mu here, going from 1 to p, while the index here goes from 1 to n. So I'm given these pairs of input-outputs, and they are randomly chosen. So just to, let's say, specify one possible distribution, let's say that sigma mu is chosen to be +1 or -1 with probability 1/2. And let's say that the inputs here can be normal random variables. They can be Gaussian variables with 0 mean and variance equal to 1. Or they could be constrained to be positive numbers. Or they could be also ±1 with probability 1/2. Basically, what I need here is some input distribution.
So you're,
OK?
So the ±1 outputs, they're not independent of the inputs. That's what.
No, OK. So I'm giving a training set here. They are independent. I just draw them randomly. And the question I'm asking here, is it possible to find a set of weights here such that actually the perceptron will map the input onto the desired output?
So the outputs are, that's an independent distribution from the distribution of the inputs?
Yes, they are not correlated. We can look at more complicated models. There are many different papers, but I'm looking at the simplest one, OK? And there are no correlation between the different mu's here. So everything is independent, OK? And the question is there a set of GI such that sigma mu will be equal to the sine of some of the IGI psi I mu for all mu? So it's a probabilistic question. OK? So the answer yes and no, and I'm interested in the probability of yes. So there is a very simple geometrical representation here. So suppose I look at the set of weights. So that would be my space here of weights. So I should be careful here and specify how the weights are what is the space of weights. So they can be, in the usual perceptron, they are just real numbers. So that means that would be simply, OK? But actually, in the example I want to discuss in more details, I will show them on the hypercube. But so far, let's suppose they are real numbers, OK?
No, I still don't understand what the problem is. Could you do that before you go on? Or
Yeah, sure.
still, yeah.
So we are given, so what I do randomly. For each mu equal to 1 to p, so p is an integer number, I draw randomly n numbers, psi I, with I running from 1 to n, which can be, for instance, ± 1 with probability 1/2, no correlation, everything is independent. And I draw an additional n+1 number, which I call sigma.
Those C's are real variables, or are they ±1? Or either way?
OK, so they can be Gaussian. I can specify different distributions. Okay.
And then what's the problem? I still don't understand it. What's the learning problem?
So the problem would be that I specify the input, I specify the output, And I want to see if I can associate the input to the output by choosing the weights of the machine, of the perceptron here.
So you give them both. Input
Yes.
and output.
Can I do that? Obviously, if the number of pairs of input-output is small, I mean, intuitively, if p is small compared to n, I've got p constraints with n degrees of freedom. That should be possible with high probability, okay, with large probability. But if p becomes large compared to n, it seems it's very complicated to do, okay? So the question is, what happens when p and n goes to infinity at a fixed ratio? And actually, this question was solved many years ago, but I just want to say one more word about that. You see, what each time so let me just write, I can see, as sigma mu is plus or minus 1, I can put it inside the sign here. And what I get is something like that. Let me write it as a scalar product between sigma mu and psi mu. It should be positive. Okay, that's the same thing. So in the following, since sigma mu is chosen independently of psi mu, I will always choose sigma mu equal to 1. Let's say what the psi mu from now on will be equal to sigma mu psi mu. Okay, I will just absorb the output inside the input here. That doesn't change anything. So what I have to do each time I choose a pattern. So an input here is called a pattern usually. So psi, this thing is called a pattern. So I will call it pattern. So each time I choose a pattern randomly in this space here, so that will be psi here, so psi 1, for instance, then of course I will, let's say, basically kill half of my space because I want J to have a positive dot product, okay, with psi. So this is not allowed anymore, okay? So J should lie on this in this half space. Then when I have a new one here, then I will kill another half, and something is left. Okay. So the question is, if I got many, many different patterns, it's very hard to have a, let's say, high-dimensional representation here. But basically, I just draw it in a very schematic way. It's clear that what I get here, the space of solution here, it will be a convex set. It can be empty, but if it's not empty, it's a convex set. And I will find some space of solution here. Everything here is not allowed. And any weight vectors inside would be a solution. So what's the probability of this, that this space of solution is not empty? Actually, this problem was solved many years ago. And to my knowledge, it was first solved by Cover in 1963. And Cover was able to compute the probability of having a solution. So that's the probability of that there is this solution. And this probability is plotted as a function of p. Let's call p over n, okay, which is the number of constraints per degrees of freedom. That seems an intensive quantity, which makes sense, which I call alpha in following. And obviously, for alpha equal to 0, there is no constraint, so probability is 1. If alpha will be very large, it will be very close to 0. So this probability will decrease. And this curve actually corresponds to one particular value of n. So I don't have a smooth curve here, but I got a set of points which correspond to rational value of p over n. Okay. But if I increase n, I will have different curves. And what Cover shows that in the large p, large n limit at fixed ratio, there is a 0-1 law at a critical value, which is alpha c equal to 2. Okay. So this is the quantity we call critical capacity, because what we are looking at is some kind of a storage problem here. So this quantity is related to the Vatnik-Chernyankis dimension, but it's not the same one. Okay, the Vatnik-Chernyankis dimension is something else. But obviously, it's related to. So what is the Vatnik-Chernyankis dimension? Just to so the Vatnik, so I don't want to waste time here because you know much more about it than I do. But just to be sure that we have same notation. So a set of, let's say, a set of input patterns, psi 1, up to psi p is called shattered if all 2 to the p outputs can be realized. What I mean by can be realized, that means that if I choose the target output here, which would be a set of +1, -1, then I will find a weight vector J which maps this inputs, this particular set of inputs here to the output. And the Vatnik-Shimodankich dimension is the largest value of P such that there exists a shattered set of input. Okay. So we see that the definition is very different here because we are looking at some extremal properties. We are looking at the best set of inputs for this particular property, while here I'm looking at some typical properties, things which happen with large probability. So it might be that for some particular machine, so here I'm looking at the perceptron, but I could look at different machines, that this DVC could be very large while alpha c is very small. So DVC does not give any lower bound to alpha c. But DVC gives an upper bound to alpha c. What can be shown is that DVC actually is larger or equal to twice alpha c n. And this comes from Sauer's lemma, because if P is larger than DVC, then not all possible outputs can be realizable, and there is an upper bound coming from Sauer's lemma about the number of possible outputs. Sauer's lemma, I don't know how to pronounce it. Sauer's lemma gives an upper bound on the number of possible outputs which can be implementable given DVC. So this is simple. Okay. So the quantity I'm interested in here during this morning is alpha c. It's not DVC, just to avoid any ambiguity. Okay. So this is all very nice, but we could ask other questions. So for instance, what happens if we look at more complicated architectures here? Instead of having a perceptron with a single layer of inputs and one single output, we could have a more complicated architecture. So for instance, we might be interested in this kind of machine. So for instance, you have inputs here, xi1 up to xin. Then there will be a first perceptron here with a set of weight j1 to jn. So that would be an output sigma 1. Then there might be another one here with a different set of weights. So that would be, or let's say, sigma prime. And then we could combine both and have the final output, which would be, I don't know, let's call it, which would be, for instance, the product of sigma prime, for instance. More complicated architectures. Then in this case, what is the value of alpha c? Do we have a 0, 1 law, and what's the value of alpha c? And the techniques that Cover used are not easily extendable to this complex problem. Okay? Or we can keep the structure of the perceptron, the same architecture, but instead of having real weights, I will say that the weights gi should be on the hypercube. That is, I'm looking for solutions of the same set of equations, but now the gi should be equal, each gi should be equal to plus or minus 1. So obviously, since I've got less degrees of freedom, or let's say less flexibility in the choices of the GIs, the alpha c we are now looking for should be smaller than 2. So what's the value of alpha c?
It's obvious that for all these machines that it's p over n, that's going to be a constant and not p over something exponential in n. Can you not?
No, I mean, it depends on how you define the machine. You can have very, strange way of defining.
It's obvious that it won't be exponential in that the number of I guess if the inputs are Boolean rather than Gaussian, because then the weights can be bounded as relatively small integers, in which case then you can make a counting argument that shows that there are most exponentially many number. You can't represent a random function on more than a polynomial number of inputs. So it's going to be somewhere in between n and n log n by counting arguments.
Yeah.
But it's not obvious that it's just going to grow linear. It's not obvious
No.
to me that it's going to grow linearly.
If with the on the hypercube, you mean, for instance? Or
On the hypercube, because
yeah.
on the hypercube, you know that the weights can be bound. The weights can be relatively small integers. When it's Gaussian, I'm not sure that there's any normal form for the weight.
Yeah. So I'm not going to give any proof of what I'm going to say here, but just calculation how it works. And actually, the idea is not only to compute alpha C. So computing alpha C is interesting, but what we would like to have is some, let's say, microscopic view or microscopic understanding about the structure of this space of solution here. So in the continuous perceptron, which is the model I just discussed, it's a very simple kind of thing, okay? But we could imagine, for instance, on the hypercube or let's say more complex architectures here, then there is no reason why this domain should be convex, for instance. It could be made of different patches here, okay? And there are many natural questions about this set of solutions here. How many different convex domains do we have here? How big are they? So what's the typical distance between two solutions inside the domain? And how can we define a distance, some kind of Hamming distance, for instance? What's the distance between two different domains here? And how do they change when the number of constraints per variable increase, for instance? So these are the questions we are interested in.
I guess here it's clear that the threshold can't be bigger than 1.
Yes, absolutely. So
That's what I was just saying. Yeah.
yes, it's a very simple bound you can get from first moment calculation. But I will come to that. I mean, just, yeah.
So why is it important to choose the JIJs on a hypercube? Is that physically natural or biological? I mean, that's just, yeah. So I mean, I'm just asking for the motivation for
Yeah.
the choice.
Okay, so there are different motivations. One comes from neurobiology. Having real values for synapses doesn't make a lot of sense. Synapses, they are composed of vesicles, so they are supposed to be some kind of, let's say, quantized in the sense that they are just multiple of some small values. So having plus minus 1 would be an extreme case where actually what you would be interested in is some set of things, let's say GI, taking values running, let's say, from minus 1 to 1, but with a finite step, okay? So it could be -1 plus some small delta, -1 plus 2 delta, and so on, 2 plus 1. So the idea that you have a continuous choice of synaptic coefficient doesn't make a lot of sense. It's just an idealization. So this case here is the extreme case. And we'd like to know, let's say between these two extremes, we would like to know this extreme situation here, and reality should be somewhere in between. And then there is another motivation, and actually, that this problem is related to the random satisfiability problem I want to mention at the end of the talk. Okay, so from now on, I will consider, so maybe I should erase here. I will consider this question here with the constraint that G1, each GI is equal to plus minus 1, okay? So that's the question. Okay, so what I consider, I define a quantity which I call the number of solutions. So given a set of inputs, psi mu, so as I said, the outputs are always equal to +1. They are just incorporated in the inputs here. I'm defining the number of solutions, which is a function of inputs, which is just the number of solutions. But I just write it as a kind of sum over all possible choice of the weights. So there are 2 to the n terms in the sum. And I will count 0 if this is not a solution, and 1 if it's a solution. So I write a product of indicator function. So I hope the notation is clear here. So it's just an indicative function, which is one if this condition is satisfied or 0 or otherwise. OK, so this number here can be any integer number, or not any, but it can be it's an integer number running from 0 if there is no solution to my learning problem, up to 2 to the n if I don't have any pattern, for instance, to store, and any set of weights will be a solution. OK? So since it can be an exponentially large number, if a number in n, I will look at the log of this number. OK? And more precisely, I would like to know what's the probability when I choose stochastic inputs here that this number will be somewhere between 2 to the n omega and 2 to the n omega plus epsilon. Should be some probability. Omega here is something which is a real number which goes from 0 to 1. There is no reason to look at different values of omega. Okay?
I'm sorry, there's no sigma here, or what?
Yeah, OK, so as I said before, the sigma can be always put in here. My nu psi mu is the old sigma mu psi mu. I can do that just to lighten a little bit the notation. OK, so that's a very complicated quantity to calculate. But I make some assumption that there is a large deviation principle here, OK? Which means that this quantity, I mean, what I assume that this quantity has a well-defined limit when n goes to infinity first, and then epsilon can be as small. And this is a function of omega, which is a rate function. Oh, yeah, sure. Sorry. Yeah, absolutely. And alpha, yeah, that's always, yeah. So this function, this is a function of alpha also. Yeah, I always keep p and n to infinity, send them to infinity as fixed ratio. OK? So what could be intuitively the shape of this rate function if it exists? Then this rate function should be defined. So it's a log of a probability. So that should be a negative quantity. And it should be something like, I do expect something like that. So omega here runs from 1 to 0, OK? And R of omega should be here. Could be a convex function. I don't have any proof of that. I mean, many rate functions are convex functions, not all of them, of course. It depends on, there's no obvious subadditive property here we can use. I don't see it, but OK. Anyway, and I expect that there will be some maximum here corresponding to r equal to 0, which would be a function of alpha. And what would be the meaning of this maximum here, of a locational maximum? That would be that if I randomly draw a set of inputs here, for instance, and then with high probability, the number of solutions of this set of inputs for a given ratio alpha here would be 2 to the n omega naught, omega 0. Up to non-exponential terms. Yeah.
So isn't it conceivable that that it be 0 at a single point and go to negative infinity everywhere else, meaning that there's a single value of omega, where you have a sharp threshold where you're almost certain to have that many solutions.
So you don't want a finite? You mean a finite width here?
Not even that is, as n goes to infinity, the width goes to 0, so it really is a single point.
It's hard to. I've got difficulties to imagine that because.
Because you're doing concentration in the log.
Yeah. Yeah.
No, I think that makes it.
Well, as I said,
You're right.
I don't have a proof that there is a shape like that, but I can show how to calculate it within some assumption. Okay? So that's not a proof. It's just that if the assumptions are correct, then we get the right shape. But
there should be a probability that's at least x exponentially small in capital N that like the should be no solution. In which case, this quantity 1 over n log, the probability will at least be some finite number, right?
Well, we were taking the limit as n goes to infinity, so the probability.
No, but some that doesn't depend on n.
No, but why would it not depend on n?
Well, there's a 1 over n next to
No, yeah, I mean, I'm looking at.
Yeah. Oh, I see. I'm sorry. I didn't
It's really a rate function I'm looking at.
So
Okay.
it should be at least finite everywhere.
Yeah.
Okay. Sorry, I didn't see the normal.
No, okay, no, I just okay. Okay, so how can we compute this function? Well, first, before we go to the calculation of this function, if we are able to calculate it and to compute the location of maximum here, then in principle we are done, because then this function omega 0 of alpha, that would be the log in base 2 of the number of solutions divided by n, then this thing here should decrease from 1 for alpha equal to 0, because everything is a solution, to it should decrease as a function of alpha. And then it goes, a simple hypothesis is that it's a smooth function of alpha, and then it goes to 0 at alpha c. Okay. So how can we compute R? So what we do is we look at the nth moment of a number of solutions. So I've got a lot of n. I've got a big N, which is the number size of the problem, a small n, which is the order of the moment here, and this curve n, which is the number of solutions. And here I mean the average over the inputs. So let me do that. So by definition, which is just the sum of all possible number of solutions of the probability of a number of solutions times the number to the small n. And if I look at, I'm interested only in exponential asymptotics here, that should be something like an integral of omega 2 to the n r of omega 2 to the n omega small n here. It's not an exact equality here because there are some leading term. I should put some plus over n here, I guess. But still, I mean, the important thing here is that when n is large, that should go to maximum of omega of r omega alpha plus n omega. Which means that if I'm able to compute the left-hand side here, and in particular, if I'm able to show that this left-hand side is something like this plus small o of n, then this function here should be related, is simply the Legendre transform of R. Okay. So now I will devote some effort in order to compute the nth moment and to get this function phi. So in particular, if we get phi, in order to find omega 0, then you see, so phi of n of alpha is just the Legendre transform with respect to omega of R, which means that omega 0 of alpha should be, if the function is differentiable, here phi is differentiable, should be the derivative of phi with respect to n in n equal to 0. Okay? Is it okay? See, if I differentiate, I just say that for large n, then I would, maybe I went too fast. I mean, if I'm able, so this equality here from between this and this comes only from the definition of R. Now, assuming that I'm able to compute this number here, I mean this quantity, and show that for large n it behaves like that, then I know that phi of small n comma alpha is equal to this quantity here. And if phi is differentiable with respect to n in n equal to 0, then I should get this. So basically, the Legendre transform is just a way to represent the same curve, but with a parameter which is the slope of the curve. So n equal to 0 corresponds to a slope equal to 0. N equal to 1 corresponds to a slope here. If you look at, so the condition for a maximization here is just simply that dr over d omega is equal to minus n. So n equal to 1 corresponds to a slope minus 1 here, n equal to 2 to minus 2, and so on. So I put this minus 1, minus 2 because we will come to that, to these values later.
So this is replica?
This is replica. Yes, I will use replicas. Okay. So I will do the calculation of phi for n equal to 1, n equal to 2, and then tell you how it can be done for any n, and under which assumption this calculation can be done, and how we get alpha c from this calculation.
So does this say that replica is justified if you make some assumption, or?
I wouldn't go too far. Yeah, so the problem here is that we are able to compute that only for, okay, I will do it only for integer value of small n, obviously, of course, because otherwise I don't know how to do any calculation, okay? Then the trick is how to do the analytical continuation, as you know. I mean, and you see it's not, no, I'm not claiming that. I mean, that just it would be just too much. Yeah, but maybe it's a way to think about it, a different way, I don't know.
You'll compute for like some small integer n and then hope it holds for all real n.
Yes, exactly. But obviously, this is not true. But we believe that it can be made true if one do it in a tricky way. Okay, which I want to show.
There's no replica symmetry rate here.
There is. Okay, so let me do it for n equal to 1. That's a trivial case. But I mean, let's do it n equal 1, n equal 2, and then any n. So n equal 1 is very simple. So what we want to compute is the average number of solutions. So let me write again the definition of a number of solutions. So that was, that's the top line here on the blackboard. So I've got a sum over all different GIs. And then I've got the product of a mu from 1 to p and the indicator function. OK, so I want to compute the average. So I can exchange the sum and the average here. OK. Then I use the fact that the patterns are independent, so I can check the average and the product. And I use the fact that they are identically distributed. So that gives only the sum of a j here of the average value of indicator function over, let's say, the first pattern or any pattern. And this average value should be to the power p. Yes?
So it's actually very simple in this case. You don't actually need lots of independence. So you say fix j, okay, then that fixes a function from inputs to outputs. Okay? So fix any inputs, and now you're picking the output at random. So the probability that your output, your
yes.
observed output matches this random output is exactly 2 to the minus p.
I agree.
So it's 2 to the n minus p.
I agree. I've got too much here in order to get this result. This is true. Yeah, no, I agree. Okay, so in this,
what you're saying generalizes. So.
Yeah, I will go to larger value of n where I think I need more. But okay, so here you see at obviously this indicator function. I mean, if I fix j and I choose a random pattern xi, then it will be 1 with probability 1/2 and 0 with probability 1/2. For what? For psi?
Using that to have some symmetric and maybe continuous distribution?
Yes, you mean, I was thinking of psi I, just the Gaussian distribution first, but we can use the plus minus 1 also with probability 1/2. That would do the same thing in the large n limit. I think it gives 1/2. So that's simply.
So in the end, you're either multiplying it by 1 or minus 1. So that's why it's always symmetric.
Yeah, well, you're saying you folded the sigmas into the sides.
Yeah.
Yeah.
So that
Okay, so I get simply this, and then the sum is 2 to the n, so I get this simply this. And this is exactly what you said before. The average number of solution is given by this quantity, and this is an upper bound to the probability that there is at least one solution due to first moment method. So for alpha larger than 1, there won't be any solution with high probability. So alpha c, if it exists, is smaller than 1. Okay, so now let's go to n equal to 2, which is more interesting. Oh yeah, sure. So now I want to compute the second moment. Okay, so the second moment will be, okay, I can just repeat the same calculation. I got the sum of a gi. So let's say sum of a j vector here, and then I got the product, the mu 1 jx. Okay, and this should be squared, and then average over the input. So I will write the square of the sum as a double sum. So I've got a sum of a j. So I put an index 1 here and an index 2. And then I just copy the indicator function. And this should be average. And as I said before, using the fact that the patterns are independent and so on, I can average here, and actually all the average are equal. So I can have just one average to the power p, and I can drop the mu index here. Okay, so it's a bit more complicated than before, but not too much complicated. So what we have now is we have two vectors, so let's say j1. And we have another one, which is j2. Let me draw it like this. And now we draw a random pattern. And we ask what's the probability that this random pattern has a positive scalar product with both vectors. Okay, and you see that what happens is that if I look at patterns which have a positive dot product with the first one, they are outside this half space. They are outside this half space or second one. And if I call theta the angle here, I have to sum all three angles here in the two-dimensional plane. So this is simply the sum of the three angles, which is pi minus theta over 2 pi. But of course, this angle theta depends on the two weight vectors j1 and j2. So instead of manipulating angles, I will manipulate overlaps. So overlap is just the scalar product. So I define the overlap Q, which is just the normalized scalar product, because the norm of j1 and j2 is square root of n. Both norms are equal to square root of n. Okay. So that means that n sol squared should be equal to the sum of the j1 and j2. And then I got, let's say, 1/2 minus 1 over 2 pi. And I get the arc cosinus of q, which is a function of j1 and j2. Okay. So now this can be computed easily because I can choose j1 as I want, and then it depends only on the scalar product. So I got the sum of a j1, which is 2 to the n, and then I have to compute how many vectors. So I choose j1 all once, for instance. How many vectors do I have for j2? So and it's just a combinatorial factor. So sum of a q here, which runs from -1 to +1, with steps of 2 to 2 over n. I got this. Okay. So now in the large n limit, I can look only at the dominant contribution here to this sum. And I will find that this is to exponential order equal to 2 to the n times some maximum of a q of some function. And the function, you can read it from here. It's just alpha times the log of the argument here plus the entropy function, okay, plus 1. So where is the maximum of a q? So it depends on the value of alpha, of course. So I've got different shapes here for different values of alpha. So for instance, for alpha equal to 0, we get only the entropy function. So maximum is obviously in q equal to 0. Okay. Just an even function of q. Now, if alpha is positive, you see that there is a bigger contribution for positive q coming from this term than coming from negative q. So the function here of q is not a symmetric function under q going to minus q anymore. So for instance, I just plotted I just a sketch here. So that would be a function for, so the function can have two different shapes. It can be something like that. So that would be q here. Maximum value is 1. 0 here. So the maximum can be in some q star, different from 1. And this happens if alpha is smaller than alpha 2, which is about 1.45. It's not an exact value, it's just an approximation. And then otherwise, you can have a maximum in q equal 1. If alpha is larger than alpha 2. Okay. So I get for q star something like that. The alpha, that will be q star. Oh. With a jump here, and the value of q star right below the jump is about 0.7. Okay, so that's the output of the calculation.
Sorry, you're going a little fast for me. What are these pictures capturing again?
Oh, okay, so I want to maximize this function here, okay, as over q. And if you plot the function f of q for different values of alpha, that would be f of q. For value of alpha which is smaller than alpha 2, and that would be f of q for value which is larger than alpha 2. Just sketch the functions, okay? Obviously, they will depend on alpha, but the overall picture is this one.
Alpha, oh, I see, that's the size.
Okay.
That's the value of p, basically.
Yes, that's p over n. Okay, so what is the meaning of q? So the meaning of q, we have found, is some kind of overlap between solutions of a problem. But it's not the right overlap we are interested in. So what is exactly the q we have computed? So the q star, or let's say the q star we have computed, if you look exactly at the calculation we have been doing here, is this quantity. So we sum over all possible weight vectors on the hypercube. We compute the dot product here, normalized by n. So it's the overlap. And then we restrict the sum over solutions only to our set of, to our learning problem. So I will get product of write it. Okay. Yeah, so that's the same here. And what we have been doing, if we have been averaging here over patterns, and if you look precisely at what we have been doing, there is obviously a normalization here, which is the same thing without the overlap here. So it's just a second moment. This is q star in the large n limit. But this is not what we are interested in, right? What we are interested in is the quantity where the number of solution squared is inside here. Okay, we don't want to average the numerator and the denominator in independent way. The true q we are interested in, as I said, if we are interested in the geometric nature of a space of solution and trying to understand it, we want to compute the overlap between two solutions of a problem, for instance. The quantity we would like to compute is something else. What we would like to compute is something like that. So I just write it briefly. Okay, you have a product of indicator function, and this should be divided by the number of solutions squared, and this should be average. Okay. So what would be the true Q? Well, we know that what.
Can I ask a question?
Yeah, sure.
So you were talking about what you wanted to compute and what the true Q is and stuff like that. You were sort of doing a calculation of the second moment, and it
Yeah.
looked like it was successful and it involved this like Q star. But now you switch gears and you're saying, what if we want to know about the average overlap between?
Yeah, so I'm saying what with the second moment we compute this Q star here, and what is the interpretation of this Q star here? Naturally, that should be the overlap between two solutions, okay? And actually, it's the overlap between two solutions if we constrain the set of patterns. If the patterns are not typical patterns, they are very highly atypical patterns, which correspond to set of patterns giving a huge number of solutions, okay? So basically, what we are on this curve here. So I'm afraid I just erased it. You remember there was this R of omega curve. That was omega 0 here. We are looking here at the region where our slope is equal to -2. So, and that there will be, so with very low probability, the log of probability this one, okay? With very low probability, we have inputs which generate or which are associated to a huge number of solutions here, much bigger than the typical number of solutions, okay? And what we are looking at are the typical overlaps between solution in this particular, for this particular set of inputs. So what we want to do is to shift here and go to the typical properties here.
But before we get to Q, I mean, can you do it for like little n equals some higher integer than 2?
Yes. So this is the point I want to go to now. Okay. How to go to generic n. So as I said, so we want to compute this quantity that would correspond to n equal to 0. So the road is to do the same calculation for any value of n. So I just want to sketch the main steps without going too much into the details of the calculation. Okay? So suppose now we look at any, or let's say at some integer n, and we want to compute the nth moment. So if you look at what we have been doing for n equal to 2, it's obvious that the generalization would be J1. We have a sum of n weight vectors now. And we have a product of the, or let's say, we have the indicator function that first pattern, the pattern should be stored by the first weight vector and so on, up to the nth one. And that should be average over the patterns. And this should be to the power p. Okay. So for n equal to 2, this is the formula which is on the top blackboard here. And this is the generalization for any n. So we want to compute that. So I don't want to do all calculation, but just explain how it works. So if we look at this quantity here, it's a bit more complicated than before. We had only two weight vectors, and the only quantity we needed was the angle, or let's say the overlap between the vector 1 and vector 2. Now it's clear that when we look at that, this quantity here, the one which is put to the power p, will be a function of all the different angles between the weight vectors, all the overlaps. So that would be a function which I call 2 to the f. So it's a different f, it has nothing to do, of the overlap. So q1, 2, q1, 3, and so on.
Isn't it going to depend not just on the pairwise overlaps, but on all subsets? You want to look at like the intersection pattern. You want to say, look at the number where all of these are 1. Look at the number where one of them is 1 and the rest are -1. And so
yes, but what I'm claiming, this is true only in the large n limit. In general, you're right. But in the large n limit, what I'm claiming is that you need only to know the overlaps.
Why? I mean, so like if that little n is let's say 3, then this point is the area of some spherical triangle, right?
Yeah.
So if it's n equals, now I can visualize. If it's n equals 4, then
are you saying because
What do you mean by symmetric?
Like all the sizes of all these different patterns are going to be the same that I was worried about.
Yeah, I mean, so this you are puzzled by this fact here.
Yeah, why just only, like Russell says, only depends on like the pairwise dot products.
I can do a calculation. It's lengthy. It's a little bit lengthy, but this is property. Actually, this is so this quantity should depend on the statistics of psi, right? It won't be the same quantity if you look at Gaussian variables, Gaussian psi, or plus or minus 1 psi. It would be different.
Approximately the same.
But for large n, it depends only on the second moment of psi. And actually, this simplifies and it gives a function only of the overlaps. If you want, I can go into the details maybe later. I mean, it's okay. I mean, this is true only in the large n limit. Otherwise, that would be wrong. Okay, so it's a function of only the matrix of overlap. Yeah.
But if the psi's are Gaussian, is it just true?
Oh, you mean exactly true for any n? Yeah, I think so. We can check that carefully later if you want. Can do the calculation. Okay, so we have an overlap matrix QAB, which is an n by n matrix, where the overlaps on the diagonal would be just 1, just by normalization. And outside we'll have the overlap QAB between so that would be QAB would be simply the dot product between JA and JB normalized by n. Okay, so if you trust me for this step here, then we have now to do the sum over the weights. And again, as we did for the second moment, we had basically the same thing. We had a function of a single overlap, and then we computed the multiplicity of the overlap here. So we can do the same thing and have a multiplicity of a matrix, which again is a complicated function of QAB, but it's a function of QAB only. So we end up with some things here, which is 2 to the f of QAB to the power p, so let's say alpha n. And then we have a multiplicity of the matrix here, which I will keep only the leading term, exponential term, so we'll have a 2 to the n times some other function, QAB here. So just to be sure, so what is this here? There will be a small overhang. What is this here? It's a sum of a J1, Jn, and I just calculate the multiplicity of this particular matrix of overlaps. So it will be
Describing the G function?
sorry. Yes, that will be that. Okay. Okay, so computing G is not completely easy here. I can define it, but then I cannot compute it before I go to the next step. Okay, so but this function should exist, okay? I assume that there is some scaling with large n or something like that. Now, what I want to do is I send big N to infinity, basically. I want to compute the dominant contribution to the sum here, which is a tough problem. We want to find the best matrix.
It's also not so easy to understand what capital F is, right?
What, sorry?
It's not so easy to understand what capital F is as well.
Yeah, I didn't want to write down the expression, but but we can go into the technical details here.
What's the expression?
We have an explicit expression for capital F. Capital F is just the average of the indicative function here.
Right.
Okay, I do have an explicit expression for capital F. But I'll show you the, okay, maybe I should have gone into more details, but I thought it would be just a real pain because. Okay, so we have expression for these things here for f, and we know that or we assume that there should be a function g. So now we have to look at where the maximum will be located. Okay, so obviously the labels of the replicas here, which we call replicas because we have just replicated small n times the initial system we had. The labels here have no particular meaning, which means that if I do a permutation, any permutation of the small n elements here, I get the same function. So I do a permutation of the lines and columns of a matrix, I get exactly the same function, right? So we are looking for a maximum here of this function, f, let's say alpha f plus g. And the assumption, which is called replica symmetry, is that the maximum, there is only one maximum, okay? You have a global maximum. There are no different local maxima. There is just one global maximum for this function. That's the replica symmetric assumption. So what does it mean exactly? It means that what is true is that if suppose I'm able to find a local maximum to this function f plus alpha g, then by permuting the elements, I've got another local maximum with exactly the same value, okay? Now, if I assume that there is a single maximum, then that means that the maximum I have found is invariant under the permutation. And the only matrix which is invariant under the permutation is a matrix where all the off-diagonal elements are equal. So the replica symmetric assumption is that this function here is maximized by a matrix QAB where all the diagonal elements are equal to Q, single element. This assumption may be true or may be wrong. Assume it's true. Then now, everything is much simpler because I can do the calculation here, which is much simpler to do, okay? I can do this calculation with large n limit, compute that, and obtain an expression for a maximum of this function.
Can you check whether or not it's true if like n is like 3? Is it?
Okay, so actually it's.
So I guess probably if it was true here.
Well,
Okay, so
for 2,
it's a bit.
true by default.
Yeah, I guess there's nothing to check. Well, yeah.
Okay, so it's tricky. It's tricky. Actually, it's for, let's say, alpha small enough, or, okay, it's true for any n, integer n. The problem is the analytical continuation to real valued n, or let's say n going to 0.
You're saying it's actually possible to prove that this assumption is true for integer n?
I don't know if it can be proven, but people in statistics, I mean, we have looked, I mean, we and many other people have looked for many, many times and never found any solution. And there are some self-consistent argument, which is basically you can show that this is actually a maximum, okay? So you can compute the Hessian matrix here and look at whether it's really a maximum or, okay. And that doesn't prove anything. That doesn't, but I mean, there are very good reasons to believe that for integer value of n, it's true.
Yeah, that's what I was just saying. If n is like little n is 3, like maybe there's like some hope of actually proving it.
Yes, but I don't think that would help for a big problem of the method, which is the analytical continuation.
Yeah, if we already believe it's true, then this would not give you any additional confidence.
Yeah, yeah. Okay, and the important point here is that if this assumption is true, then a lot of things can be done. In particular, for instance, while n, small n here is clearly an integer number because it's just the size of a matrix, then once you have done this assumption here, n becomes a real parameter. So for instance, you have a lot of terms in the calculation which are things like this, you know, sum over a smaller than b, or QAB. So obviously here, QAB is a matrix, a and b go from 1 to n is an integer number. You cannot do anything with that. But if you assume that all the diagonal elements are equal, this is just simply q times n minus 1 over 2. And here, let's say, with some ball behavior, or let's say, I don't know, you can take n going to 0, I mean, or whatever. I mean, it's okay. But as I said, the main point here is here. That's whether it's true or not is a difficult question. So I don't want to go into all details, but let's say if you follow this line of calculation, then you can compute R of omega, and get omega 0. You can compute phi, compute the first derivative here, and let me show you what is the expression for omega 0. So omega 0, function of alpha, where we still have an optimization of the two different parameters, q and q hat. And I just write it to show that it's possible to get expressions. It's not only something on the blackboard, okay? So dz here is the Gaussian measure. Okay, so it goes from minus infinity to plus infinity, so real axis. Log of 2 cosh of z plus alpha dz log of dy, and the lower bound here is not minus infinity, it's z is equal to q1 minus q. Okay. So the q we have here is the q I was interested in. The q hat I've got here is some intermediate of calculation which is used in order to compute g here. So if I was considering the initial perceptron problem where the weights are continuous, I wouldn't need q hat. Because when I look at this quantity here, so this is the quantity I want to compute, then that defines a measure over the j's here. And for continuous j's, this is a Gaussian measure. Okay, and we know everything with QAB on this measure. For j's on the hypercube here, we still have a Gaussian measure, but there is no simple way to compute the covariance matrix of a Gaussian measure when you are on the hypercube, when you know, maybe I'm confusing here. Basically what I'm saying is that, suppose you have j, suppose you had that. What I'm saying is very simple. And you normalize, okay? Just normalize over the same thing, and you compute J8 over GB. If the measure here is over real numbers, you know that what you get here is just Q hat minus 1, just the inverse matrix, right? And this should be equal to QAB. So which means that if you impose the overlap QAB between the weight vectors, you know what is the weight you put here in the Gaussian measure. If you sum here on the hypercube, there is no simple relation between Q hat and Q. So this is why we have a Q hat here to optimize over. It's more complicated. Anyway, so this can be done. And what you get is omega 0, as I said before, which is a decreasing function of alpha. And it goes down at alpha, it vanishes 0.833 and so on. So there is no proof that this is the right alpha C. You see how it obtained that. I mean, it's. So
you wait a minute. So you assumed that your symmetry is unbroken.
Okay, so I assume that the symmetry is unbroken at least up to alpha C.
Okay.
So now what happens after that? So that's an interesting question. So I just want to say a few. So what happens after that is that we were actually expecting that if I look at Q, you know, this is what I got for n equal to 2. Then for n equal to 0, this is a 0.833. This goes up to, it's about 0.5 at the critical point here. And then maybe it jumps to 1 here, but what does it mean? Because if we are above alpha c equal to 0.833, there is no solution anymore. Okay, so what does it mean, this curve here? So it means that actually we could look, instead of looking at the decision problem, whether there is a solution to the set of constraints or not, we can look at the optimization problem. What's the highest number of constraints I can satisfy altogether? So instead of counting the number of solutions, I can count, or let's say I can weight all possible weight vectors with a weight which is, let's say, x, which is a dummy variable, to the number of satisfied constraints, or to the number of unsatisfied constraints, let's say. So I can consider some kind of generating function, g of x, which is the sum over j equal to plus or minus 1. And then I put a x here. That's my variable, new variables. And here I sum over mu 1 j dot psi mu. Now, is not satisfied. Okay? So if x is equal to 0, I should go back to what I had before, right? The number of solutions. If x now is not equal to 0, I got a way to, or let's say if I send x to 0, but I don't take it equal to 0 from the beginning, I should get the minimal number of constraints which are not satisfied. So we can repeat this calculation with x, any x. And what we get is some kind of phase diagram. So usually in physics, we don't use x, we use temperature. But that's the same thing. So x is exponential minus 1 over t, where t is temperature. So t equal to 0 means x equal to 0. T equal to infinity means x equal to 1. So we don't care about whether the constraints are satisfied or not. So now we still have alpha here, but we have another parameter t. And so far, we were looking only at this t equal to 0 line. And there is this critical value here. And in fact, you can extend the calculation and find that there is a line here, where in this region, omega 0, which would be the typical number, so we can compute for given t, you can look at the average number, or let's say typical number of constraints which are satisfied, and see by how many different weight vectors they could be satisfied. Okay, that would be an extension of the omega 0 we had before for the decision problem. And we thought that this number is positive here, and this is equal to 0 here. And obviously, this is particular on this line here, because on this line here, there is no solution anymore. But still, we can define with x equal x positive and then send x to 0, we can define what happens on this line here when we reach the line from this region of the plane. And so, for instance, what happens is that, so we can go to larger value of alpha c, and for the larger value of alpha and alpha c, and we get effective, but there are two values of q. There is an analytical continuation of this one. So two values of q. So what do they mean, these two values of q? So they tell us something about the shape of a space of solution. So in this region, if I look at the hypercube, I consider only the space, let's say the set of the corners of a hypercube which are solutions. There are typically, if I pick two of them randomly, they will have an overlap q, which is, you see, I mean, this curve here, which depends on alpha, obviously. While if I am, and there are many of them, an exponential number of them. While if I am in this region here, I don't have an exponential number of them. Only a small number of them. They are still very far away from each other with this q note here. Let's say q here. And I've got a q equal 1 telling me that the solutions are just very, it's a very strange, it's a little bit complicated to explain here. Maybe in the remaining part, I will explain to you how it works for the integrated amplifier model. But that's just a trace that there were many solutions. All of them disappeared, except a few isolated solutions, isolated in the sense that very far away from each other. And we go back to the interpretation of this q1 equal to 1 here. So in this region, the replica symmetric assumption I mentioned before is wrong. Okay? It's clearly not a good solution. And the solution which is commonly adopted by people was found by Parisi about 30 years ago in a different context. That was for a different problem, but still the concepts are the same. Where instead of having all of diagonal equal to the same value q, you have blocks. So on the diagonal, we always have 1, just by definition. So outside the blocks, we have the same element Q, but inside the block, we have a different element, Q1. And by properly choosing the size of the blocks and extremizing over Q and Q1, we can have an understanding of what is going on in this highly constrained region here. So maybe I can show in the, I've still got about 20 minutes, something like that. I can show you in the second part how this kind of structure naturally arises when you look at problems where time is important.
So these Q's often one, because you think if you have a solution that satisfies all of the constraints, then like an extremely close and Hamming distance solution would also satisfy all the constraints.
Yes, exactly. So I will show that.
Sort of said them already, but
Yes. But the question is, it's true that if you have so suppose you have a solution, you change just a few GIs, you are likely to have another solution. Okay, but there are very few ways of changing only one GI. You have n ways. Certainly, if you want to get an exponential number of ways, you have to go far away at large Hamming distance. And the question is whether you have to, it's favorable to stay very close to each other, so you lose a lot in entropy in the sense that you don't have many combinations, but still you are sure that you are very close to a solution, or you should go very far away. And so Q1 equal to 1 is not something obvious. That may happen in some cases. In other cases, for instance, at small alpha, that doesn't happen. That doesn't mean that there are no close solutions. Obviously, there will be very close solutions. What I mean is that if I pick up only two of them, they won't be close to each other, which is what I mean, okay? But obviously, there will be very close solution in this huge set of solutions.
So is it possible to do the calculations when you assume it has this more complicated block structure?
Sorry?
Is it possible to do the calculations when you assume it has this more complicated block structure?
Yes, absolutely. So for some models like the Shannon quadratic model, you have to just iterate this construction an infinite number of times. So it's become much more complicated. Actually, what is amazing is that all this approach, which can be, very strange for mathematicians, Parisi was able to find solution of a Shannon quadratic model in the beginning of the 80s, and he found the free energy, which is, or let's say the average energy of his model, and that was proven to be correct by Talleyrand just a few years ago. So not that the approach is correct, that the outcome of the approach was correct, which is something different, okay?
You need multi-step. It's not two-step, though.
So in this case, it seems that only one step is okay.
Oh, really, one step?
Yes, that's a conjecture, yes. So it's very close to the random energy model.
Yeah.
It seems that one is okay.
And are there rigorous results for the high temperature phase?
Not that I'm aware of. There might be, but I don't know.
Because of course for spin glass it was done long ago.
Yes, yes. Okay, so I just want to say a few words about the more complicated model, which is the time-dependent model. So far we assume that the only important information in the spiking activity of the neuron was the firing rate. But in fact, this is not true. So we need something more complicated. So the model we consider now is kind of integrate and fire model. So let me explain how it works and briefly how all the techniques I've shown can be adapted to this model and what are the differences. So the model is called tempotron, which is a modification of perceptron just to, let's say, emphasize the importance of the issue of time here. And so here is the input. So now you still have a simple architecture, sigma. And but now the input is not just a real number. It's a function depending on time. So here's time. So let's say we have time is between 0 and some big T here. And if I look at input number n will sometimes be silent most of the time, and then there will be a spike, and there will be a lot of spikes here, and then nothing, and another lot of spikes here, and so on. And this is input number 2. We'll get maybe some simultaneous spikes, or maybe nothing, and then another one, and so on. So that's the So now we have a spatial temporal input. So how is the neuron computing the output here? So the rule is supposed to be some kind of, let's say, a realistic rule, or let's say highly simplified, but still not too bad from a biological point of view. So the neuron has some internal variable, which is the potential, which is the difference of potential between the external and the internal part of the membrane of the neuron. And the potential may increase as some inputs are received and sum up with some positive weights here, if J1 is positive, for instance, or the potential may decrease if an input from neuron 2 is received and G2 is negative. So there will be a summation of the inputs. But the summation is not done over the whole time horizon here. It's done only on some slices. So let's be more precise. The potential at time t will be a sum over all different inputs, weighted by the weights here, of a sum over all the different spikes emitted by input number I, with some kernel here, memory kernel. Maybe I should, let me call it C because I need K later on. So what is the memory kernel? Memory kernel is something which tells you that if a spike is emitted by neuron I, when the L spike is emitted by neuron I at time TIL, then suppose, for instance, Ji is positive, then the potential should increase, should have some positive contribution. So C, as a function of tau, C of tau, should be something which is 0 just by causality for negative tau. And then it should do something like that.
Should there be a C sub L? Or what is C?
So C is this function here. Okay.
It's a fixed function.
It's a fixed function. So for instance, you can say that it's, let's say you have one exponential here, and another you have an exponential increase here. So for instance, we can choose C of tau So you have two different time scales. So the first time scale tells you how long you have to wait in order for the inputs to actually produce some increase of the potential. And then how long you have to wait in order to have a relaxation or just forget about the input. So that would be the two time scales here.
But no, I'm not understanding. So is that? So I thought you said you stored up potential rather than.
No. I've not said. So far, I've not said how the output is computed. I'm just saying that there will be an internal variable for the neuron, which is this potential here, and then I have to say how the output is computed. So you are given an input. This is the input, a set of spiking times here. Here are the weights. Suppose you know the weights, then the neuron will have this potential at time t. The function is given here.
So I'm still not understanding. So TIL is.
So TIL, so that would be Ti equal to 2, L equal to 1, Ti equal to 2, L equal to 2. L is the index of a spike, and I is the index of the input. Okay?
Okay.
So each time an input enters at time TIL, then it will be, there will be some contribution in the potential, which is weighted by this weight here.
So somehow it remembers the neuron doesn't just keep just one number that's the current charge. It remembers the time every single pulse was received.
It remembers it for some time, and then it decays. Yeah.
In independent counters or something.
Yeah.
No, but it's decaying so close to 0 that maybe you can ignore it after a bit.
Yeah, I mean, it decays after time tau d. What happens if you look at the neurons at time, this time here, everything would happen before, doesn't matter. Okay, there is a decay here, which makes sense. I mean, it's much more realistic than the perceptron. And now, so what happens for the neuron? How does the neuron decide its output? Then you look at the potential here as a function of time, between time 0 and t, and the potential will do something like that. And there will be some threshold here that you fix, some arbitrary threshold. if the potential remains below threshold, the output is always equal to -1. If at some point it becomes above threshold, so that's another trace here, then the output is +1. So the outputs will depend on time also, and so it will be +1 here and +1 here, otherwise it's always -1, okay? And the final output of the process will be, we'll consider that the neuron has been active or was active. The potential has crossed the threshold at least once during the 0t time interval. Otherwise, it was always silent. So the final output will be +1 here for the red curve, and it will be -1 here. Is it okay for a definition of model? So it's not a linear threshold function anymore. It's more complicated. Because it depends on yeah.
And this agrees with the experiments you showed us with the salamander eye?
Well, it's a bit too much. It's certainly much more realistic than the perceptron. You can't sell the perceptron anymore to people doing experiments, okay? This one, they can listen to you for a while, maybe, okay? In the sense that it's much closer to the integrate and fire neuron, which is, let's say, an abstract version of a Hodgkin-Huxley neuron, which is well established by your physical model for a real neuron. Okay, so it's not realistic, but the idea that there is a potential, a threshold mechanism, and the idea that you have some integration time here, constant, and the decay time, everything is correct. This should be in the model. Now that there might be many other things which are not in this model. That's a problem. Okay. Okay. So I'm looking at the extremal properties of potential here. If the maximum potential is above threshold at some time, then the output will be +1. Otherwise, the output is -1. Okay. So the question is, what's the value of alpha c for this model? So I don't want to enter too much into details, but I just maybe, yeah, I've got 10 more minutes. I just want to say a few words about the value of alpha c. So I first simplify the problem and consider a discrete version of it. So here you see the weights can be real numbers. So I don't put, I mean, they could be on the hypercube, but let's choose real numbers just to have a life a little bit simpler. What is very complicated here is the architecture of the model. Okay, or let's say how the output is defined from the input. So let me just tell you what a simplified version here, which I call discrete tempotron. And then you will see that asymptotically in some regime, actually this is equivalent to this model. So here's the input. So I is here. And now I cut time into discrete numbers. I will have some time slices. So L will be equal to 1 here, up to L equal to K here. Okay. So on. And in each slice, so that would be, let's say, neuron number I here, and time slice number L, I will have one spike or no spike. So I choose to put a spike with the Poisson rate. So 0, 1 with the Poisson rate, which is, let's say, 1 over k, where k is the number of time slices. So that on average, I've got one spike, for instance. So if that doesn't matter too much, we can put other than 1 over k, other things, it doesn't matter. As you will see later. It doesn't matter in the large k limit. So we have this model here. So that would be the input pattern. So now we have an extra dimension. So we have 3 indices now. You have I, the number of inputs, mu, the number of patterns, and L, the time. So it's a matrix. That's your input patterns. The output will be plus or minus 1. And you have p different matrices. And you want to know if you can store them or not. So that's a problem, okay? So actually, the important point here is that the domain of solution is not guaranteed to be convex anymore. It's not as simple as the perceptron.
Sorry, did you say how it produces output?
Yes, so let me tell you in this model here.
If it's bigger than a threshold, or
Yes.
if BT is bigger than
Exactly, yeah.
Oh, okay.
So let me repeat it here. I will look at the maximum over L of the sum of a Ji psi IL mu and compare it to threshold here. Okay, and that would be the output. Psi IL mu is the element here of this matrix IL for the Muse pattern. So it's a simplified version of the model here, because here in the discrete version I sum all the spikes coming in one time slice, and then when I move to the next one, I have basically forgotten what happened before. So I kill a lot of correlation. Well, here I've got correlation with a windows shifting like that. So it's more complicated. The first model is more complicated than this one. This one is simpler. But actually for large K, I will just want to give you a... OK, so I can redo all the calculation I've shown before. They are much more complicated, but they can be done along the same principle. The principle is very general. So what we are interested in here is, as I said, we have these patches of solutions. So we want to know what's the typical overlap between two solutions in one domain. What's the typical overlap between two different solutions in two different domains? And what is the number of domains? And the first thing I should say is how I define a domain. And I define a domain by looking at patterns which should be mapped on +1. If a pattern is mapped onto -1, I know that the potential should be below threshold at any time. So there is no ambiguity. If the output is +1, it means that the potential should go above threshold at some time. But I don't specify the value of the time. So there are 2 to the k minus 1 possibilities, right? Which I call internal representation. So an internal representation is just specifying at which time, when I've got a plus pattern, the output of a neuron should be plus.
Sorry. So you're saying you interpret, if any time in the interval the neuron fires, you interpret that as a +1. And if it never fires within the interval, it's interpreted as a -1.
Yes. You can change that. You can say if it fires
still looking at P random inputs,
yes.
and then starting it from some initial condition like 0,
Yes.
and evolving it over a fixed amount of time.
Exactly. I'm still doing the same thing. So the internal representation tells you if I cut into k different slices here, whether the potential should be above threshold here, or it should be minus here, above. So in this case, I would have 3 spikes for the output neuron. So that's one possibility for a plus pattern. So I've got 2 to the k minus 1 possible internal representation. Possible, that doesn't mean that I can realize them. It just means I can write them down. Now, for some of them, there will be some solutions to the problem. For other ones, there will be no solution. And what I call domain is a set of weights corresponding to one particular internal representation. If you think about it a little bit, if you specify the internal representation, what you have is just the perceptron problem we had before. Because if you specify exactly at what time the output should be plus or minus and so on, you have k different perceptrons, just one after the other one. So since the critical capacity of a perceptron is 2, then it means that all internal representations are possible up to alpha equal to 2 over k. Then if I look at the log of number of internal representation, I should have log of 2 over k minus 1. That would be per plus pattern. And then it should decrease and reach some alpha c here, which depends on k. And this quantity here is basically the log of the number of domains I am interested in. So we can redo the replica calculation. It's a bit more, it's more complicated than the one I've shown before. But I just want to say a few things about the results. So in this case, replica symmetry is always broken. And what do we get? So we get values of the overlaps, and we get values for alpha c. So I just want to show the values we get. Yes. I will comment. I will be a bit more specific about that. It depends on the value of alpha, but it's always broken in the region of it. I mean, close to alpha c. So basically, what we get is that if we are in a region where we don't have a full solution for any value of k. If you ask me what is the value of alpha c for k equal to 10, I can't tell you. But we have an asymptotic solution for large k, which I hope is correct. So n goes to infinity first. P on n goes to infinity at fixed ratio alpha. Then we send k to infinity, or let's say very large k. And we get alpha c of k equal to log k over 2 log 2 plus subdominant term. And we get that in this region, so when alpha is of the order 1, so log k is here. So 1 would be, so this goes to 0. As k goes to infinity, this goes to infinity. So now if I am in a region where alpha is of order 1, then I get value for q1. So q1, as I said, would be the typical overlap between two solutions here. And this is like 1 minus some constant here over alpha squared log k. q0 is like alpha log k over k. And the number, this curve here is very simple. It's just log k minus alpha, so it's 1 minus alpha log 2 in this region here.
This is under the assumption that there's a single level of symmetry breaking?
Yes, but we believe this is correct for k going to infinity, while when k is finite, for instance, k equal to 10, this is not correct. And there should be an infinite number of replica symmetry breaking steps, like in the Schrödinger compact model. And this is just too complicated. So, okay, so just why do we get these results here? I can give you a very simple argument why we get this scaling 1 over log k, for instance, where it comes from. It comes from very simple, I mean, you can understand it in a very hand-waving way with extreme value theory, for instance. So we are looking, so suppose we choose, so if I look at the potential here at some time, or let's say in a slice here, so the potential VL, so I can always choose the scaling of the weights and the scaling of the threshold, so that the average value of that will be equal to 0 and the variance will be equal to 1. And in this case, what I had to do is look at the maximum value of k Gaussian random variables. Okay, and you know that if you have k Gaussian random variables with normal laws like that, the largest one will be of the order of square root of log k. Okay, plus some fluctuation of the order 1 over square root of log k. So that will fluctuate here. So this is, suppose I found a solution. So or suppose I got a set of weights. I present the patterns here. I compute all these VLs, and the maximum would be something like that. Now suppose that this pattern is a plus pattern. So that means that the threshold should be here, around here. And for my particular pattern, I am above the threshold here. Now I draw randomly another set of weights with an overlap Q with the first one. And as this is the question you asked before, I mean, if Q is very close to 1, then I should have a solution. If Q is going to be smaller and smaller, then the probability of having a solution will decrease. So the question is how the probability of having a solution will decrease. And what I claim here is that the probability of having a solution decreases very fast with Q. And in fact, it's basically, it's very small when Q is smaller than this number here. And the point is that if I draw randomly a second set of weights, G prime, such that g prime dot g n is equal to q, this number here, so I look at in the same time slice, in the same time, I look at the value of potential here. On average, it will be, so if I call it Vmax, that will be Q Vmax. And there will be some fluctuation here of for the square root of 1 minus Q. It can be computed. I mean, it's not very complicated. Which means that as soon as square root of 1 minus Q is larger than the typical fluctuation you would expect around the threshold here, which is order 1 over square root of log K, then you don't know what it's going to do with the second machine. You don't know whether the pattern will be classified as a plus or minus. So I'm going fast here, but I mean, the idea is this. So that explains the value of Q1. And in fact, we can do much more things. And the idea that extreme value, what matters here is only extreme values of the distribution of a potential, means that a lot of details in the calculation are not important. Because you know that the statistics of the extreme value of random variables is very robust against a lot of details. So in particular, in the model we had before here, we can redo the calculation. So we can compute, for instance, the covariance here. And the covariance will be a function of the things here. Okay, so that's which I call a covariance, which is a function of tau. And basically, the important thing is that if you have correlated Gaussian variables, okay, with continuous process here, then you know basically you can use the result of a discrete set of independent Gaussian variables with the value of k effective, which is the time times the square root of a derivative dc over d tau in tau equal to 0. Okay, this is known for Gaussian stationary processes, which in our case would be simply t over square root of tau I tau d. Now, if you put realistic numbers here, so the duration of presentation of pattern for real neurons, you put these numbers here, which is about 1 millisecond. This is about 10 milliseconds, 100, something like that. You get that in k is of the order, I don't want to say stupid, k is of the order of, let's say, 30, 50, 100, while the number of connections can go up to, let's say, 1,000. So in real life, this model here, you would expect that the assumption that n is large and k is large but much smaller than n is correct. Obviously, what is bad here in this theory is that the convergence is very slow, and the asymptotic results are not sufficient. We would like to have much more than that, but we can't. Okay, so I will conclude. So I think I don't know if I have convinced you with all this calculation. I mean, there are a lot of assumptions and so on. But this is a very flexible method which can be applied to many different systems, not only these learning problems, which has been applied by many people to many statistical physics problems, and can be useful to get some insights about the structure of a space of solutions here, which I think might lead to conjectures, which might be of interest to you. And I want also to say that actually it's closely related to the K-stat problem. Random K-stat problem, Russell and Paul know very well. If you look at the perceptron with plus of minus 1 weights, then there is a very simple mapping. If instead of having patterns where all the components are plus or minus 1, you say that only k components are plus or minus 1 and all the remaining n minus k are equal to 0, then basically you have a random K-stat. But it's even more complicated than what I've shown before. Okay, but so all the works which were done in the statistical physics community actually were based on this kind of approach for random K-stat problem. And one final aspect about that I want to say is that, so if this theory is correct, we have an idea about alpha c of k, but we don't know of any algorithm which is able to reach this threshold, this critical capacity. So it's one thing to know that with high probability there is a solution, and then it's another thing to find the solution. So there are some learning algorithms, but we don't understand whether they are good or not. Simulation seems to show that they are not too bad, but we don't have any understanding, quantitative understanding on the probability of success and how far they can go. I mean, to which value of alpha they can go.
differ from KSAT though, right? Because in this problem you can decide efficiently if there is a solution.
You mean in
Not in the time model, but just the original model.
yes.
Either
No. If you take
or just the
j equal to plus minus 1.
It doesn't matter, right? It's deciding if a linear program is.
No, with j equal to plus minus 1.
If j plus minus 1, yeah.
No, you can't. Yeah.
What does this actually say about learning? I mean, in that, so you're saying saying something about the representational power of a perceptron, and somehow it says what the minimum number of samples you need before you have any evidence that what you're learning is a perceptron. But what does it? Is it actually interesting to look at algorithms for this problem? In that, would they actually be learning algorithms?
So I'm not sure I really understand the question. I mean, here I wasn't looking really at a learning problem. I was learning random things, okay?
Right.
But you would like to learn things which are produced by a machine, for instance, to see if you are able to find back the weights of a machine which has generated the inputs.
So I guess, so this random function, which is what you're looking at, is sort of the null hypothesis.
Yes.
So if you can learn, if your algorithm only works in the range when a random function would have a perceptron representation, that really means you're overfitting the data and not learning at all.
Yes.
So it's only when you go beyond that and use the fact that the data is itself generated by a perceptron or something similar that you're actually making progress.
Yes. I agree.
So is there any value to designing an algorithm to solve the problem for random noise, for random functions? Would that actually help you with non-random functions? Or is that just interesting from the point of view of other random satisfiability functions?
But you would think that the algorithm is different? Or you would think that the performances of the algorithms are different?
So is this an interesting algorithmic question or just an
Oh.
interesting combinatorial question?
Pretty interesting algorithmic question, but not one that is, good, but not one that's really related to learning if you do assume some structure and data.
Yeah, I mean, algorithms for random k-stat is an interesting algorithms problem.
Right.
Now, if it's algorithms for random k majority or something, that's,
Right. Here it's algorithms for k majority where k equals n.
Yeah.
Something like that.
It's a problem.
Yeah.
You don't mean that in a negative sense.
No,
Yeah, I mean-
in a positive sense. Yeah.
You mean, is there any interest beside the fact that we don't know of a good algorithm for it? I mean, you want a strong motivation.
Okay, I guess you said it's the learning problem.
Yeah, okay, maybe
Is it really,
I overstated it. I would say it's a storing problem. I don't know how to call it. Okay.
yeah.
Yeah. That would have been, yeah, you're right.